This is Calculus Part 13 of our Aeronautical Engineering course. You may have noticed at the end of Part 12 that I made a mistake. We were talking about the area of a propeller being 0.175 meters squared. So the thrust of the propeller, or the lift, whatever you want to call it, is going to equal coefficient of lift times air density times the area times velocity squared over 2. We were plugging and chugging. Coefficient of lift is 1.0. The air density is 1.225 kilograms per cubic meter. The propeller's area, plainly written right in front of me, is 0.175 meters squared. And I wrote down 0.175 meters. So I should have put a little squared right there. And the velocity, 144 meters per second, which all gets squared divided by 2. And as you can see, our units work out now. Kilogram, meter squared again, because all that gets squared, per second squared, divided by meters cubed gives us kilogram meters per second squared, which is what a Newton is. Our answer, that times that times that times that times that again, equals 2,223 kilogram meters per second squared, or Newton. Okay, let's move on. Let's say we have a Cessna 150 propeller that's turning 2,000 revolutions per minute and maintaining straight and level flight at 60 knots. Okay, that's what the pilot's operating handbook says is the best glide speed. For instance, well, when your engine shuts off and you need to land somewhere, if you glide at 60 knots, you can glide further than you can gliding at any other speed. Okay, what is the propeller's coefficient of lift, or coefficient of thrust, if 2,000 RPM will keep you going at 60 knots? Okay, if we use the 57.7% method of calculating our propeller thrust, we'll assume that all the propeller's area is located 57.7% of the way from the shaft center to the tip. A Cessna 150 propeller has a diameter of 68 inches, so its radius, the distance between the center of the shaft and the tip, is half that, 34 inches. Multiplying this radius times 57.7% gives us a distance of 19.62 inches. In other words, if this is our propeller, okay, and it's 68 inches from there to there, and it's 34 inches from there to there, well then 57.7% of the way from the shaft to the tip will be 19.62 or 63 inches, something like that. Okay, we determined in our last lesson that we could assume that all the area of this propeller is right there at 57.7% of the way from the center of the propeller to the tip. Okay, let's assume that the propeller's area equals its chord times its diameter. We figured it was 4 inches chord from there to there on average. Its diameter was 68 inches, there to there. Okay, so its area is going to be that times that, 4 times 68 inches squared, or 272 square inches. That's what you get when you multiply 4 times 68. Okay, the propeller speed at 57.7% of the radius, the speed here at 2,000 RPM is 104.4 meters per second. Okay, we've done this calculation before. We figured the tip speed. We said 2,000 revolutions per minute times 2 pi is number of radians per minute, and multiply that by that distance will give you the circumferential distance per minute. Okay, so let's say our prop speed at this spot, 57.7% of the way from the shaft to the tip, is equal to our 2000 RPM times 2 pi radians per revolution, so that many radians per minute, times 0.577, or 57.7%, times the radius here, which is 34 inches. Okay, and that's per minute. So prop speed is equal to 246,527 inches per minute. Okay, and let's get that in meters per second. So let's turn our inches into centimeters. So we multiply that by 2.54 and it gives us 626,179 centimeters per minute. Okay, we move our decimal point 2 spots from there to there, and we get 62 meters per minute. Well, now let's divide by 60 and we get 104.4 meters per second. That's the speed of our area of our propeller that we're assuming is all right here at this spot at 57.7% of the radius, or 19.62 inches from the center. As I mentioned earlier, the pilot's operating handbook for a Cessna 150 says 60 knots is the best glide speed, the speed that gives the greatest glide distance. The altitude versus glide distance graph in the POH, the pilot's operating handbook, shows that a glide ratio of 8.5 to 1 can be achieved. If the gross weight of the airplane is 1,600 pounds, the drag will be 1,600 divided by 8.5, because the lift to drag is 8.5. So 1,600 pounds divided by 8.5, this is the lift, equals 188 pounds of drag. And that's the least amount of drag you can, well, that's the drag you'll have at 60 knots. Okay, let's turn that 188 pounds into newtons and figure out what the coefficient of lift or coefficient of thrust of our propeller is. Okay, remember how a pound was equal to 4.45 newtons? Or you could say, we can say 188 pounds times, well, we have 1 kilogram is equal to 2.2 pounds. Okay, so that'll turn our pounds into kilograms. And then we can multiply that by acceleration due to gravity, which is 9.8 meters per second squared. And that'll give us 839 kilogram meters per second squared, or 839 newtons. Okay, so you can multiply 188 times 9.8 and divide it by 2.2, or you can just multiply it times 4.45, same thing. Okay, and now let's calculate the propeller's lift coefficient. Okay, we know that the thrust of 188 pounds, or 839 newtons, instead of writing newtons, let's write kilogram meters per second squared, so we won't forget what our units are here. That's what a newton is, kilogram meter per second squared. Okay, 839 of them is equal to our coefficient of lift times our air density, which we'll assume is standard, 1.225 kilograms per meter cubed, times our wing area, 4 inches by 68 inches, is 0.1755 meters squared, times the velocity of the spot that's 57.7% of the way between the shaft and the tip, which we figured was 104.4 meters per second, and all that's in parentheses squared, and all that's over 2. So upon punching all this out, let's see what we get here. Okay, 1.225 times 0.1755 times 104.4 times 104.4 again, because it's squared, divided by 2 equals 1172. So our coefficient of lift is going to equal 839 divided by 1172. So let's divide this by 839, see what it is, and then hit our 1 over x button, and we get our coefficient of lift equals 0.72. Oops. Yeah, remember how we figured our coefficient of lift when we had static thrust sitting on the runway holding the brakes and getting 500 pounds of thrust. We figured our coefficient of lift back then was 1.0. As we're moving through the air, it's 0.72, and that makes sense because you have a higher angle of attack when you're sitting there still. The propeller's taking a bigger bite. This is the end of our calculus lesson, the end of the series, but we've got a couple of minutes left on this video, so I might as well comment on an assumption I made back in part 12 about having 500 pounds of static thrust with a 100 horsepower engine. That's based on the old saying that you get about 3 to 5 pounds of static thrust per horsepower, so 100 horsepower would give you somewhere between 300 and 500 pounds of static thrust. And since a Cessna 150 flies rather slow, I figured it was probably more on the high end of this 3 to 5 because power is equal to force times distance per unit time. And if your distance per unit time isn't much, then your force is going to be a little higher. So we can look at the POH, Pilot's Operating Handbook, and see that we have a 735-foot takeoff roll for a Cessna 150. Generally lift off at 60 knots, so the average speed is going to be 30 knots. Well, 30 knots is 50.6 feet per second. We just threw in all the conversion factors there to get that. Okay, so 30 knots is that many feet per second. That's our average speed over the 735 feet. So 735 feet divided by 50.6 feet per second tells us that it takes 14.5 seconds to take off in a Cessna 150. Okay, but we got it up to 60 knots, which is twice this, 101.2 feet per second. Okay, so 101.2 feet per second divided by 14.5 seconds is 6.98 feet per second, or feet per second squared, and that's 0.218 G's because 32 feet per second squared is what 1 G is. So the airplane weighs 1,600 pounds, so 0.218 times 1,600 equals 350 pounds of thrust that we average taking off. So that assumption of 500 pounds of static thrust probably wasn't all that erroneous. See ya.